When building software for high-stakes decision-making, the idea of a final delivery is a dangerous myth. You can spend months constructing a rigid system only to watch it get crushed the moment it meets the chaotic reality of a live market. This diagram illustrates the standard, linear, traditional approach to software development. Notice how it relies on strict sequential stages. You lock in a fixed scope, build step by step, and hand off a finished product at the end of the line. That structure looks stable on paper, but it assumes the business environment is static. In reality, market pressures fluctuate and executive priorities pivot. By the time you hit that final delivery wall, the original parameters have usually changed, creating a massive drop-off into high risk. Applying rigid linear models to dynamic decision problems guarantees system obsolescence on the exact day it launches. A successful decision support system requires a completely different geometry. Looking right, we see the evolutionary approach. Instead of a dead-end staircase, it's a continuous, adaptive loop. This model operates on three explicit tenets: taking short development steps, gathering direct user feedback immediately, and using repetitive design cycles to constantly refine the tool. In this environment, a software product is never finished. It is only temporarily stabilized so decision-makers can use it while the next iteration is already being planned. This diagram breaks down the iterative cycle. First, abandon building everything at once to isolate a critical subproblem. Then, execute a rapid microcycle. Develop a small system, get immediate decision-maker evaluation, and based on real-world usage, constantly refine and expand its capabilities. This graphic details the two massive advantages of shrinking the development cycle. By focusing on microsystems, you secure a short development time and you keep the initial financial risk incredibly low. This iterative speed serves as a calculated strategy designed specifically to minimize the cost of inevitable course corrections. But rapid iteration introduces a serious engineering challenge. If you are constantly rewriting and expanding a system every few weeks, how do you prevent the entire software architecture from collapsing under technical debt? This diagram shows the required specialized architecture. A DSS must be decoupled into modular blocks: a data management base at the bottom, a heavy-duty model management core for analysis, and a front-end dialogue subsystem to handle user interactions. Because these components are physically separated in the backend, engineers gain a massive tactical advantage. They can completely swap out a complex predictive algorithm in the model management core without breaking the interface the executive is using on the front end. True software evolution is a structural impossibility unless the underlying architecture is designed specifically to isolate and absorb continuous change. Once that modular backend is in place, the static framework spins into motion, driven by a highly specific procedural engine. This diagram illustrates that engine, the 8-phase system lifecycle. It forms a continuous circular track rather than a straight path to a finish line. Every rotation of this cycle begins with the planning phase. As this pyramid illustrates, planning cascades downward. You must define the overarching organizational goals at the top before you can accurately specify the hardware and software strategies at the base. With the strategy set, a new feature request moves rapidly through the loop, researching the approach, analyzing feasibility, designing the update, building the module, and finally implementing it for the user. Completing those 8 phases doesn't mean the project is over. It simply means the engine has completed one revolution and is preparing to spin again. This forces a redefinition of the end of a project. Instead of keeping a depreciating system on life support, DSS maintenance requires aggressive observation. Implementation becomes a data-gathering step, feeding user requirements directly back into the next adaptation phase. In DSS engineering, deployment serves as the trigger for the next cycle of learning and adaptation. This chart visualizes the constant transition between supporting a system and upgrading it, a continuous ecosystem of feedback and response. The friction of changing user needs provides the mechanical force to turn these center gears, driving the next phase of adaptation. When we look at this blueprint modeling a multi-year lifespan, a clear geometry emerges. As the text notes, DSS development is not a straight line, it is flexible engineering. Completing the 8-phase loop puts you one level higher, operating with a smarter tool. A rigid software system will always break under the pressure of a changing market. A decision support system survives because its underlying architecture places the decision maker precisely in the center of an infinite, highly flexible loop of improvement.